Hello everyone. Welcome back to my course Fundamentals of Thermodynamics, Essential Knowledge for Engineers. In this video we will talk about wave and flow phenomena, Doppler effect, and isentropic relationships. Also, I will be thankful if you give me feedback about this course to make it better and more useful for you. Please write down your thoughts in the comment section or reach out to me via the email provided in my profile. When an object moves through the air, it disturbs the air particles around it. These disturbances travel outward in all directions, and they move at a specific speed known as the speed of sound. We call it the speed of sound because sound itself is not a physical object. It is a sensation created in our brain in response to tiny pressure variations that travel through the air. These variations move in the form of waves, which spread outward from their source. Whenever these waves reach our ears, our brain interprets them as sound. To better understand this, imagine sound as a repeating wave pattern. The distance between two successive wave crests is known as the wavelength, while the number of waves that pass a given point in 1 second is called the frequency. These two quantities are directly related by the speed of sound. If the frequency is high, the wavelength becomes short. If the frequency is low, the wavelength becomes long. Our brain translates frequency into what we call pitch. Higher frequencies correspond to higher pitched sounds, while lower frequencies create lower pitched sounds. Similarly, shorter wavelengths correspond to higher pitch, and longer wavelengths correspond to lower pitch. An important point to remember is that the speed of sound in a given medium does not change with frequency or wavelength. Instead, it depends only on the state of the medium itself, for example, its temperature, pressure, and density. This is why sound travels at different speeds in air, water, or metal, but for a given medium, the speed of sound remains constant regardless of how the sound is produced. Because the speed of sound depends only on the medium and not on the source, interesting effects occur when a sound source itself is moving through a uniform gas such as air. In this case, the moving object keeps generating sound waves that still travel away from it at the speed of sound. If the object moves slower than sound, the waves can spread out ahead of it. However, the movement of the source compresses the waves in the direction it is traveling. This means that in front of the moving source, the waves are closer together and their wavelength is shorter. Behind the object, the opposite happens. The waves spread farther apart and their wavelength becomes longer. Doppler effect. Now, because wavelength and frequency are related, this compression and stretching of sound waves affect what our ears hear. As the object approaches us, the wavelengths reaching us are shorter, which makes the frequency higher, and we hear a higher pitch. As the object passes by and moves away, the waves lengthen, the frequency drops, and the pitch becomes lower. This shift in pitch due to the motion of a sound source relative to an observer is called the Doppler effect. The Doppler effect can be described mathematically. If we denote the speed of sound in the medium as a, the velocity of the source as u, the original frequency emitted by the source as f, and the frequency heard by the observer as capital F when the source is approaching, we can write down the equation. The equation is the frequency heard by the observer equals the original frequency of the sound multiplied by the speed of sound in the medium and then divided by the speed of sound minus the velocity of the approaching source. This equation shows that as the source approaches, the denominator becomes smaller, making the observed frequency higher than the original. On the other hand, when the source is moving away from us, the waves spread out and the frequency decreases. If we denote the frequency heard as the source leaves as capital F, then the formula is: the frequency heard by the observer equals the original frequency of the sound multiplied by the speed of sound in the medium, and then divided by the speed of sound plus the velocity of the receding source. In this case, the denominator becomes larger, which reduces the observed frequency, and we hear a lower pitch. Real-world examples of the Doppler effect. A very common and familiar example of the Doppler effect is the sound of a passing ambulance or police siren. When the vehicle is moving toward you, the siren seems to have a higher pitch than usual. But as soon as the vehicle passes and starts moving away, the pitch noticeably drops, even though the siren itself is producing the same constant sound. What your ears are detecting is the change in frequency caused by the compression and stretching of the sound waves due to the vehicle's motion. Let's hear this example. Another example can be experienced at airports. When a jet flies overhead, the roaring sound changes sharply as the plane passes by. Before it reaches you, the sound waves are squeezed together, producing a higher pitch. As soon as it moves past you, the sound waves stretch out and you hear a much lower pitch. The Doppler effect is not limited to everyday sounds either. It also has important applications in science and technology. For instance, astronomers use the same principle to study stars and galaxies by observing how light waves stretch or compress as celestial objects move toward or away from Earth. Similarly, police use radar guns to measure the speed of moving vehicles based on the Doppler shift of reflected radio waves. Isentropic flow relations. In compressible aerodynamics, the behavior of gases can be described by a set of equations known as the isentropic flow relations. These relations become important when gas flows at speeds close to or greater than the speed of sound, because at those speeds, we cannot assume the density of the gas remains constant. Instead, compressibility effects must be taken into account. To begin, let's define the main variables. Here ρ is the density of the gas, P is the static pressure, T is the static temperature, and R is the specific gas constant. The velocity of the gas is represented by V. The speed of sound is denoted as A. The cross-sectional area of the flow is catal A, and the Mach number is m. The dynamic pressure is symbolized by Q, while gamma is the ratio of specific heats, the ratio of Cp to Cv. Total or stagnation values of pressure, temperature, and density are given by Pt, Tt, and ρt, respectively. Finally, A star refers to the cross-sectional area when the flow is choked, meaning the Mach number equals 1. The key equations with meaning. 1. Mach number definition. Equation 1. The Mach number is equal to the speed of the flow divided by the speed of sound. In words, the Mach number is simply how fast the flow is moving compared to the speed of sound. Analogy. Imagine you're running on a moving walkway. If you run at half the walkway's speed, you're at Mach 0.5. If you match the walkway's speed, you're at Mach 1. 2. Speed of sound. Equation 2. the speed of sound is equal to the square root of the specific heat ratio multiplied by the pressure divided by the density. It can also be expressed as the square root of the specific heat ratio multiplied by the gas constant multiplied by the temperature. In words, the speed of sound depends on how tightly packed and energetic the gas molecules are, which comes down to temperature and the gas properties. Analogy. Think of sound as people passing a message in a line. If people are standing closer, higher density and pressure, or if they respond faster, higher temperature, the message passes quicker, just like sound. 3. Isentropic relation between pressure and density. Equation 3. The pressure divided by the density raised to the power of the specific heat ratio is a constant. Equivalently, this constant can be expressed using total conditions as total pressure divided by total density raised to the power of the specific heat ratio. In words, when flow is isentropic, pressure and density follow a fixed mathematical relationship. Analogy. It's like compressing a balloon gently without losing heat, pressure, and density rise together in a predictable way. 4. Pressure, temperature, density relationship. Equation 4. The ratio of static pressure to total pressure is equal to the ratio of density to total density raised to the power of the specific heat ratio, which is also equal to the ratio of temperature to total temperature raised to the power of the specific heat ratio, divided by the specific heat ratio minus 1. In words, the ratios of static to total conditions, pressure, density, and temperature are linked by gamma. 5. Dynamic pressure. Equation 5. The dynamic pressure is equal to 1/2 multiplied by the density multiplied by the square of the flow speed. It can also be written as 1/2 multiplied by the specific heat ratio multiplied by the pressure multiplied by the Mach number squared. In words, dynamic pressure measures how much motion energy the air has compared to when it is at rest. Analogy. Stick your hand out of a moving car window. The force you feel is caused by dynamic pressure. Faster car, more pressure. 6. Pressure ratio as a function of Mach number. Equation 6. The ratio of static pressure to total pressure is equal to 1 plus 1/2 multiplied by the specific ratio minus 1 multiplied by the Mach number squared, all raised to the power of negative specific heat ratio divided by the specific heat ratio minus 1. In words, at higher Mach numbers, static pressure drops more relative to total pressure. 7. Temperature ratio as a function of Mach number. Equation 7. The ratio of static temperature to total temperature is equal to 1 divided by 1 plus 1/2 multiplied by the specific heat ratio minus 1 multiplied by the Mach number squared. In words, the faster the gas flows, the cooler its static temperature compared to the stagnation temperature. 8. Density ratio as a function of Mach number. Equation 8. The ratio of density to total density is equal to 1 divided by 1 plus 1/2 multiplied by the specific heat ratio minus 1 multiplied by the Mach number squared raised to the power of 1 divided by the specific heat ratio minus 1. In words, density decreases with higher Mach number because the flow stretches out as it speeds up. 9. Area Mach relation. Equation 9. The ratio of the flow area to the choked area is equal to the quantity 1/2 multiplied by the specific heat ratio plus 1, raised to the power of negative of specific heat ratio plus 1 divided by twice the specific heat ratio minus 2. multiplied by the quantity 1 plus 1/2 multiplied by the specific heat ratio minus 1 multiplied by the Mach number squared raised to the power of specific heat ratio plus 1 divided by twice the specific heat ratio minus 2 and then divided by the Mach number. In words, this equation connects the duct area to the Mach number. When the flow is choked Mach 1, the area is A star. Analogy. Think of water flowing through a garden hose nozzle. As you squeeze the nozzle smaller, the water speeds up until it can't go any faster. That's choking at Mach 1. Physical meaning. As a gas flows through a tube, the molecules are deflected by the walls. At low speeds, much less than the speed of sound, density hardly changes, so the flow can be treated as incompressible, like water. But when speeds approach the speed of sound, density varies a lot, and the gas compresses and expands depending on pressure and temperature. We analyze this behavior using conservation of mass, momentum, and energy, while assuming an isentropic, reversible, adiabatic process. Isentropic means no entropy change, so it is idealized and lossless. In reality, it's like imagining perfectly smooth, frictionless flow. The total or stagnation conditions, total pressure, temperature, and density are the values you'd get if you brought the flow to rest without losing energy. For example, if you face into the wind while cycling, the extra force you feel is related to stagnation pressure. The Mach number is the key to unlocking all these relations. If you know Mach, you can calculate pressure ratios, temperature ratios, density ratios, and even the required nozzle area. Conversely, if you measure something like the pressure ratio, you can work backward to determine Mach number and all other properties. Isentropic flow relations work for smooth changes like gradual nozzle expansions or contractions. But if the flow path changes suddenly, for instance, if a nozzle pinches too quickly, shock waves form. These are abrupt compressions where entropy increases, so the isentropic equations break down. Instead, you need the shock relations, normal or oblique shocks, which account for irreversible processes. Okay guys, now let's have a little quiz. The quiz consists of 3 questions. I'll give you 10 seconds for each one, and then I'll show you the correct answer. Let's start with the first question. Question 1. When a sound source moves toward an observer, how does the observed frequency change? The correct answer is it increases because the sound waves are compressed. Question 2. Which of the following factors primarily determines the speed of sound in a medium? The correct answer is the properties of the medium, such as temperature, pressure, and density. Question 3. In an isentropic flow, which of the following statements is true? The correct answer is pressure and density follow a fixed mathematical relationship. Unlock the world of aerospace engineering with my other expertly designed courses. In Aerospace Engineering, Basics of Aviation Engines, you'll explore the different types of aerospace engines and how they perform, giving you a strong foundation in the propulsion systems that power modern aircraft. Then, take your knowledge to new heights with aerospace engineering, aerodynamics, and structures, where you'll dive into the design and performance of aerospace structures and their aerodynamic behavior. Finally, expand your expertise with aerospace engineering, avionics, and aerospace systems, where you'll learn about the critical electronic systems that control and monitor modern aircraft, bridging the gap between engines, structures, and flight systems. Whether you're a student, aspiring engineer, or aviation enthusiast, these courses will equip you with essential knowledge to understand and contribute to the future of aviation. Join hundreds of learners and start building your aerospace journey today. Thank you guys for watching this video. If you have any questions about this lesson, feel free to ask me in the comment section. I will answer as soon as possible. We can continue to the next lesson and learn about basics of thermodynamics, temperature, energy, and entropy. See you in the next video. Bye.